Hi everyone, welcome back to our statistics class notes. We're now moving into section 7.3. We are on page 101 of our class notes. Section 7.3 is the central limit theorem for sample proportions. So the objectives of this section are to identify the conditions needed to apply for the central limit theorem for sample proportions and use the central limit theorem for proportions to describe the sampling distribution of a sample proportion and to find probabilities. Okay, so recall that we did 3 simulations on the last set of videos on the end of section 7.2 notes. And I was kind of giving you an idea of where we're heading. In those simulations, I was supposed to be giving you an idea of where we're heading as far as understanding the sampling distribution of the sample proportions. Okay, so here's the objectives of the central limit theorem for sample proportions. Used to estimate proportions in a population. Okay, that's what we're trying to do. And it tells us that if some basic conditions are met, the sampling distribution of the sample proportion is close to the normal distribution. That's like kind of a minor mathematical miracle, to be honest with you. All right, so the central limit theorem for sample proportions says the following. If we take a random sample from a population, and if the sample size is large and the population size is much larger, then the sampling distribution of p hat, right, sample proportion, is approximately normal with a mean of p and a standard deviation of this standard error, which we introduced in the last section also. Standard error is a standard deviation of the sampling distribution. So it's the square root of p times 1 minus p over n. If you don't know the value of p, you can always substitute the value of p hat as an estimate for the mean. Okay. So 3 conditions for the central limit theorem for sample proportions. 1, the sampling must be random and independent. 2, you have to have a large sample. Now, what do I mean by large sample? You basically have to have the sample size n large enough so that the sample expects at least 10 successes, yes, and 10 failures, no. In other words, if we ask a yes-no question, we want to know what's the proportion in our sample that say yes. You have to have at least 10 of them that say yes and at least 10 of them that say no. So whatever we can call a success or a failure doesn't matter. There's no negative or positive connotation to the word success or failure or yes or no. It's just whatever we're looking for the proportion of. I have to have at least 10 in one group and at least 10 in the other group. Okay? The successes, or if I call those the yeses, if I want to estimate what I would get out of my sample, it's n times p hat. Now that's a formula for it. If I'm looking at my sample, I can just count up how many people said yes. But I take n, which is the sample size, multiply that times p hat, which is the proportion of my sample that said yes, then that needs to be bigger than 10. If I take my sample size n and I multiply it times 1 minus p hat, that would be the proportion of my sample that said no to the question, then that has to also be bigger than or equal to 10. Now, a big population means that if sampling is done without replacement, the population must be at least 10 times larger than the sample size. So remember, this was a result of our second simulation where I was showing you a sampling distribution of p hat for 10,000 samples of size 10 drawn from a population with p equals 0.25. Remember, I had 25% walkers in my sample. Right? I had a sample with a population of 1,000, 250 of them were walkers. I had a population of 1,000 with 250 of them walkers, meant the population proportion of walkers was 0.25. So this does not satisfy condition 2. The sample was not large enough. My sample's of size 10. There's no way I could have had 10 walkers and 10 runners in that sample when the sample size itself is only 10. So the sample size was too small, and thus the distribution, which was starting to be unimodal but not symmetric. It's a little skewed to the right, so it was not normal yet.